Hi, students. The previous or the original Chapter 19 lecture, after I did quality control, I discovered that it became garbled after about 3 hours, 51 minutes, roughly. So the previous video should be good till 3:51:00, if you look at the video. And then last 1:55:00 or 1 hour and 55 minutes was garbled. I'm not really sure what happened. I think it might have had something to do with a thunderstorm going through. But anyway, I'm going to redo the last part of this video. So to my chagrin, where we left off, the last problem we did was problem 19.38. All right, and so in the previous video, the last thing I did in the previous videos, in the previous video, the last or the point where the video went bad was just after the completion of problem OpenStax 19.38. All right, so I'm continuing from there. All right, now we'll start off with OpenStax 19.39, where we left off. All right, so again, to remind us, 19.38 was a problem where we had 2-point charges. So we had a point charge. So I guess 19.38. I guess let's just kind of remind ourselves what 19.38 was, because 19.39 actually hinges upon 19.38. So OpenStax 19.38. We're asked to draw equipotential lines around a charge configuration where there are 2-point charges, and we were given the electric field lines. All right, and so we determined 1938 we have 2-point charges at Q1 and Q2. Remind ourselves here, and those 2-point charges, we saw that we had 2 electric field lines emanating Q2 to Q1, and then here's a couple more. Then actually, I think these were drawn a little differently. Let's see. A little more toward the back. All right. And then so that's 4, and then we're going to draw another 12. That's 4 going into here. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Number of field lines is important. All right, so in drawing equipotential lines, I guess I'm kind of redoing number 19.30, I suppose. So what do? Well, you draw equipotential lines. They must intersect electric field lines perpendicularly, as we determined. Not supposed to cross. All right. Anyway, they intersect perpendicularly. One of the things you can determine is that what we know is that given that the number of field lines, so number of field lines Q1 divided by the number of field lines Q2 is equal to 16 divided by 4. So again, the magnitude of the electric field, or the magnitude of the electric charge is, from which the field emanates, is going to depend. I mean, the number of field lines. The greater the field, the greater the number of field lines. And so we see there's a ratio of 16/4, which means that's a ratio of 4:1. So the charge Q1 hence has a magnitude compared with charge Q2 of 4/1. Now, given that electric field lines emanate from Q2 and terminate on Q1, we can also determine that Q1 is negative and Q2 is positive. So Q1 would be a negative 4Q. Q is some number. Q2 would then be a positive Q. All right, so that's what we can determine from this picture. We know from the number of electric field lines that number of electric field lines is dependent on the size of the charge, or basically the size of the charge determines the size of the electric field. Remember, Coulomb's law for a point charge is K cap Q over R squared. All right, and so the greater the charge of interest, the greater electric field. So you see that, a charge of negative 4Q is going to have 4 times the magnitude of the electric field than a charge of positive Q. All right, so the electric field is going to be directly proportional to the charge of interest. And so again, the number of field lines is proportional to the magnitude of the electric field. When we draw electric field lines, the greater the electric field, the greater the magnitude. And of course, the greater the number of field lines represents it. So we would see that there would be four times as many electric field lines for a charge that has a magnitude of 4Q compared with one that has a magnitude Q. And given that electric field lines again terminate on a negative charge, we automatically see that that Q1 should be negative, and then of course Q2, the electric field lines actually emanate from Q2, so we can determine that's positive. Okay, so that was the gist of problem 19.38. 19.39 depends on 19.38. All right, and so again, keeping 19.38 in mind, let's now continue where we left off and go on and do 19.39. And it's kind of where the previous previous video went bad. All right, OpenStax 19.39. All right, so that says sketch of equipotential lines. A long distance from the charge is shown. In figure 19.28, and the picture I just drew. Indicate the direction of the increasing potential. All right, so we'll talk about that in a moment. All right, sketch the equipotential lines. A long distance from the charges shown in figure 19.28. Indicate the direction of the increasing potential. All right, so we're going to look at the limit of going far away from these charges. All right, so the previous problem, we're looking at the charges more closely, and the fact that they were separated and there are two different charges actually mattered. But far away, the two charges look like a point charge. Look like a single point charge. Of charge, say negative 4q plus q equals negative 3q. All right, so far away, the electric field lines are radially inward. Okay, because they're going to terminate on an overall negative charge, and the equipotential lines are concentric circles. All right, so that's what we see. It looks like a point charge. And overall, it doesn't really matter that it's two separate charges that are negative 4q and q. From far away, it looks like an overall charge of negative 3q. The electric field lines look like they're radially inward, and equipotential lines are concentric circles. Now the question is, which direction is the increasing potential? Well, again, the direction of increasing potential is along the electric field line. So the direction of the electric field lines so I guess we're asking about increasing potential, right? So electric field lines actually let me draw this out real quick and draw what it looks like. All right, so can I say this in words? So far away, what's the picture look like? far away from the charge configuration. So we see what it looks like is we have a negative 3Q charge. Electric field lines are radially inward. Okay, there's your electric field. And your equipotential lines always have to be perpendicular to electric field lines, so it's going to form a circle. So there are, as I said, concentric circles. Draw a couple. Now, indicate the direction of increasing potential. Well, the increasing potential is always going to, so again, electric field lines remind ourselves always point toward decreasing potential. They always go from higher to lower potential. Hence, the direction of increasing potential would be outward. The direction of increasing potential is radially outward, the opposite of where the electric field lines go. Electric field lines always point in the direction of decreasing potential, higher potential to lower potential. All right. Next problem, OpenStax 19.41. Okay, this one says sketch the equipotential, sketch the equipotential lines in the vicinity of the negatively charged conductor in figure 19.29. I'll draw that. How will these equipotentials look a long distance from the object? Okay, so sketch the equipotential lines in the vicinity of the negatively charged conductor in figure 19.29, which I'll draw in a moment. How will these equipotentials look a long distance from the object? All right, so draw the picture. So it looks kind of like an ellipsoid. All right, I have more of a concentration of negative charges on the end caps, and they're a little more smoothed out along the length of it. And so, of course, what has to happen here? Well, it's negatively charged, so electric field lines must always come. It's a conductor. That's another thing to keep in mind. It's a conductor. So this is a conductor. All right. So being a conductor, what does that mean? Well, it means that the electric field lines have to come toward the negative charges, and they must be perpendicular to the conductor. So I must draw them so that they're perpendicular to the conductor. They cannot it's not perpendicular. Something like that. And they're all coming inward. These are the electric field lines. Every charge gets a field line. Okay, that's your electric field. And of course, to draw the equipotentials, I need to draw lines such that the line is always perpendicular to the electric field line. So I'll do my best. Actually, they actually connected. All right, well, there you go. Get the idea. All right. Far away, the conductor will just end up looking like a point charge. It'll look like a negative point charge. With radially inward electric field lines. It's negative. And equipotentials and concentric circle equipotentials. Fit this here, equipotential lines. Again, far, far away, anything looks like a point charge. This will be a negative point charge. Whatever this charge happens to be, it'll be just like a negative point charge with this total charge. It'll look like a negative point charge, hence it'll have radially inward electric field lines and concentric circle equipotentials. All right, let's look at 19.42, open stacks. Okay, this says sketch the equipotential lines. surrounding the two conducting plates. In figure 19.30. Given that the top plate is positive, and the bottom plate has an equal amount of negative charge. You certainly indicate the distribution of charges on the plates. Is the field strongest where the plates are closest? Why should it be? Okay, 1942, I'll draw the picture in a second here. Sketch the equipotential line surrounding the two conducting plates in figure 19.30, given that the top plate is positive and that the bottom plate has an equal amount of negative charge. Be certain to indicate the distribution of charges on the plates. Is the field strongest where the plates are closest? Why should it be? Okay. All right, so let's draw this out. All right, open stats. I erase this. 19.42. All right, so here's the picture. Two plates that are not parallel, equal size. All right, so the top plate is positive, bottom plate is negative. Now, remember that Coulomb's law tells you that the electric field strength and also the force too. I mean, you multiply by a test charge, for instance. So, well, actually, force between two charges. Let's just write that out. It's inversely proportional to the square of the distance. So the smaller the distance, the greater the force, and also the greater electric field. And so you would see a greater concentration of charges where they're closest. And then when they get further away, they'll be more spread out. So I would expect that I would have more of a concentration of positive charges. And then as we get more spread out, or as we get further away, the charges will not be as concentrated. All right. So electric field lines, again, these are conductors. All right. So these are conductors. Remind ourselves. So it means electric field lines must emanate and terminate, from a positive charge to negative charge, and they must leave the surface of a conductor perpendicularly and enter the surface of a conductor perpendicularly. And so it's going to look something like this. Oops, not like that. All right, so here's your electric field lines. Again, starting on a positive, terminating on a negative. So what might equipotential look like? Well, I could draw like one here. Maybe draw another one over here. Yeah, I mean, that's probably good enough. All right, so now, okay, so the next topic, we leave the concept of the equipotentials, and this is really where we had left off in the previous lecture. So the next topic, and really like the last topic of this chapter, is what is called capacitors. All right, so what I'm going to do is I'm going to try to draw a picture of of two parallel plates. Give an example, right? So again, we've been talking about parallel plates being our favorite electrical arrangement, and we have also stated that one plate's positive and the other plate has an equal amount of negative charge. I never actually told you how to do that. Well, now I will. Drawing is not my forte. Okay, so we have two plates. Now we're going to say that we'll have plate A. Oh, sorry. We'll have two plates. Well, again, one's going to have a positive capital Q charge. The other one is going to have a negative capital Q charge, right? So, I mean, I've been drawing plates all along, but how does that work? Well, there's going to be a battery that's going to connect the two. The battery also has a positive terminal and negative terminal. So from the positive terminal is a wire that extends over to the back of charge Q1. And on the back of charge Q2, will be yet another wire, and we form a little circuit. All right. So that's how we apply a battery. This is a battery. You apply a battery and you get the separation of charge in this manner. Now these parallel plates become what's called a capacitor. So the parallel plates parallel conducting charge conducting plates become a capacitor. Okay, so we're going to study 3 circuit elements in this class. All right, so 3 circuit elements that we'll study in this class. I mean, there are more circuit elements, but the three we're going to study in this class will be the capacitor, a resistor, and an inductor. All right, we're studying the capacitor now. We'll study the resistor in chapter 20, and then the inductor we'll study when we talk about magnetism. All right, so question is, what is a capacitor? Right off the bat, let's discuss what that is. All right, so a capacitor is a device used to store electric charge. So you can see there's electric charge on these plates. And that is the point of a capacitor. Capacitors have an application ranging from filtering static out of radio reception to energy storage and heart defibrillators. Okay, and really I can create a capacitor by just putting two conductors near one another. So one can create a capacitor. One can form a capacitor by placing two conductors close to one another but not touching. So I could take any two conductors, put them together. It could be any ugly looking arrangement of two conductors. Long as they're not touching, they can form a capacitor by time. But the thing is, if I want to actually be able to compute, anything with the capacitor, I need to have symmetry. So a situation like, for instance, these two parallel plates is a very nice situation. There's very high symmetry. So what's the relationship now? One of the things we have to always understand when we talk about a circuit element is how does it relate to voltage? So clearly the important characteristic with a capacitor is charge. When we talk about resistors, the important characteristic is going to be what's called the electric current or flowing of charge. We're going to want to understand how that relates to voltage. Here we have charge. We want to understand how it relates to voltage. Well, in general, charge on a capacitor charge Q on a capacitor relates to the potential difference across it say potential difference V across it by right today. Q equals CV. Okay? C is called the capacitance. So what are the units of capacitance? Again, that's a very important term. A capacitor has capacitance. Okay? So units of capacitance are going to be, let's see, let's solve for it. We have C as Q divided by V. So it's going to have to be coulombs. Well, let's see here. It's going to be C as Q over V or coulombs per volt. So it's right over here. So again, C is called the capacitance. The units, so solving here, we have the C is Q over V. So that would be coulombs per volt. And when you see a coulomb per volt, when you put that together, that becomes what's called the farad. That becomes 1 farad, named after the great Michael Faraday. So we honor Michael Faraday with that. Michael Faraday was one of the great physicists in electromagnetic theory. In fact, when we talk about Maxwell's equations, one of the great Maxwell equations will be named after him. Michael Faraday is an example of a person, I mean, he's an example that you could be a great physicist without being good at math. Michael Faraday was not known, for his mathematical skills. However, he was one of the most brilliant experimental physicists in history. In fact, James Clerk Maxwell took his data and to understand, Faraday, what's called Faraday's law. So one of the laws of electromagnetic theory is called Faraday's law. So again, the farad honors him. A farad is actually a very large unit of capacitance. We will generally use what is called microfarads or nanofarads. So we generally don't use a farad. A farad would be a very, very large capacitance, even though it's just 1, or 1 farad doesn't seem like much, but it actually is a very large capacitance. All right. So what we like to do is understand how to compute capacitance in general. And so that's most easily done with symmetry. So we would like to compute capacitance. And this is most easily accomplished in high symmetry situations, like parallel plates. Parallel plates actually 2 concentric cylinders. It's another mean, most likely the capacitor that you would pick up in the lab would be cylindrical. It would look like a little cylindrical, a little cylinder, a little wires coming out. Or two concentric spheres. When I say concentric cylinders, I really mean cylinders that are centered about the axis of the cylinder, all right? So, for instance, a good example, you know, in our case, would be parallel plates. Possibly, you know, two conducting cylinders, so a cylinder inside of another cylinder. So here is a conducting cylinder, and on the outside is another conducting cylinder with air in between. Or you could have, let's say, a sphere, and then another sphere, and there's air in between. All right, so again, two conductors, two concentric conductors, and in between here's air, or in here, air, or of course in here is air. All right, so again, two conductors that are in close contact, and again, we have the ability to actually do the calculation because of high symmetry, and my pictures are not very good. All right, so what I want to do, I mean, the only calculation we're going to do in this class officially is for the parallel plates. I want to show you with the parallel plates how the process of how we actually can compute the capacitance of a parallel plate capacitor. All right, let's do that. So I'm going to draw my parallel plate capacitor looking a little bit different. So in my picture, I'm going to have a plate here. Cannot draw it, eh? All right, I think it. There's one, and there's another plate right here. Okay, so the upper plate will have, I'm going to make it the same size. The upper plate's going to have positive charge. Bottom plate, negative charge. Every positive should have a corresponding negative. And of course, electric field lines should be parallel to each other and perpendicular to the conducting plates. And they leave a positive and go to a negative. Or do the best I can. They're supposed to be perpendicular. There's your electric field. All right. Now, what do I know so far? Well, I know for a parallel plate arrangement, we've said this before, that V equals ED. Again, this relationship between voltage and electric field, or potential difference across the capacitor. And again, there's a distance D between the plates. Right, so the potential across the parallel plates is equal to the electric field times the separation. All right, so that again, this is only true for a parallel plate arrangement. This is not true for any other arrangement, any other scenario. Okay, so we do know this much. We also know, in general, that Q equals CV. And I also said that. Now those are two, I mean, again, this is in general. This is only for a parallel plate arrangement. This is true in general. So what I want to do is I want to be able to actually write Q equals CV. So the thing I want to be able to do is I need to be able to relate
the electric field to the charge. I need to be able to connect these two equations together, and I really want to be able to express the capacitance. So I need to be able to combine these two, and so I need to be able to basically combine the charge. You know, I mean, the only thing that they would have in common would be the charge, and so I need to be able to express the electric field in terms of the charge. Well, we only know how to do that in one situation at this point, and that is for a point charge. You know, for a point charge, we know, this is all we know so far. For a point charge, we know that the electric field is KQ over R squared. So we know the relationship between electric field and the charge of interest for a point charge. We did not know this relationship for any other configuration, and I need to know it for the conducting plate. So again, we have a positive charge, capital Q, in the upper plate, and a negative charge, negative capital Q, in the bottom plate. So I need to somehow understand what the relationship is between charge and electric field. All right, and so how do we do that? Well, when you go to electromagnetic theory and you want to solve a problem, well, you want to go to your fundamental equations. You know, you want to go to what's called the Maxwell equations. So far, we only know one of them, and that's Gauss's law. So we're going to use Gauss's law of electricity to derive the relationship between the electric field and the charge. All right, so how do we use Gauss's law again? Well, we need to draw a Gaussian surface about the charge of interest. So I'm going to draw a very tight, normally in physics, we refer to this as a Gaussian pillbox, as it's called. We're going to draw a very tight Gaussian surface about the positive plate. So very, very tight. And remember, this is called a Gaussian surface. Now, remember, these are conducting plates. So the charges are actually on the surface. There never is charge. Even though my drawing is not very good, there's never charge inside of a conductor. It's only ever on the surface. And the positive charge and negative charge are going to be as close together as possible. They're going to be on the internal surfaces. All right? And so with a Gaussian surface, we applied Gauss's law across the Gaussian surface. So what is Gauss's law again? So Gauss's law of electricity. It says we want to divide the area in which the electric field lines emanate. We want to divide that area into little tiny patches, differential areas. And what we want to do is we want to sum up over all those differential areas. Area 1, area 2, area 3, all the way, area I, for instance. All these little differential areas. So if I take a look at one of these, I take a look at the positive plates. You know, what do I really want to do? Well, I know the plate has an overall area, capital A. I do know that. What I want to do is any Gaussian surface, I want to divide it into differential little tiny areas. Little tiny areas. Try to make them as equal as possible. All right. And so divide this up as finely as we can. Little tiny areas, and let's say this is area I. Now remember, in physics, an area is actually a vector, and the direction is in the normal direction, right? So what Gauss's law says is I want to sum up for each one of these little areas. I want to take the dot product of the electric field line, and I want to make sure the area is so small that I only have to worry about one electric field line there. Electric field line, electric field at that area, the direction of that electric field, dot product with the area normal. So I want to sum up all of these E sub I dot A sub I's across this. So remember, A sub I is an area normal. It is, an area is given as, you know, length times width as usual, but it has a direction. It is perpendicular to the surface. This is called an area normal. vector is perpendicular, that's what normal means, to the surface. I want to add all of these up, all the way across the positive plate. And by a miracle, this is what the law of the universe is that it's equal to the enclosed charge, the charge that's enclosed in the Gaussian surface, divided by this constant of the universe of permittivity of free space, epsilon naught. Again, that's what Gauss's law says. It's one of the laws of the universe. We don't know why it's true. It's always true. That if I add up, right, if I add up all of the E sub I dot A sub I, electric field dot product with the area normal, all the way across a surface in which electric fields emanate, that's equal to the enclosed charge, the charge enclosed within the Gaussian surface divided by epsilon naught. Now we're going to find out that this calculation is most easily done, of course, when there's high symmetry. Now, of course, you really want to employ Gauss's law with integral calculus. You really want to make those differential areas so small that they're infinitesimal and there's an infinite number of them. So this summation, we add up the calculus style. We have what's called the surface area, the surface integral of E dot dA. And that on the right-hand side is still the same. Q enclosed divided by epsilon naught. All right, but we're not doing integrals in this class, and quite frankly, we don't need to for this. We're going to find out this is actually a fairly simple problem. All right, so we know a number of things that can simplify our life. First of all, the electric field emanating from a conductor is perpendicular to the surface of the conductor. Okay, that's always true for a conductor. The other thing we know about this arrangement is that for the parallel plates, the electric field line, the electric field is uniform, means it's constant in magnitude. And the field lines are parallel. It's a nice, perfect, uniform electric field. All right, and we know something else. Well, if the area normal is parallel, then, the area normal is perpendicular to the surface. The electric field lines are parallel to the area normals. What's that mean? That means that if I have E sub I dot A sub I, remember what a dot product is. It's the magnitude of the first vector, E sub I, times, again, I took the hats off, times the magnitude of the second vector, A sub I, times the cosine of the angle between them. Well, the cosine, if they're parallel, the angle between them is 0. Cosine of 0 is 1. That means I could take the dot product calculation. Again, try to separate these two here. I take the dot product calculation, I can turn it into a nice, easy calculation of the magnitudes. So I can actually replace it with simply the calculation of E sub I times A sub I. So I can take the dot product and replace it with just an ordinary multiplication of the magnitudes. So with all this information, I can do the following. First of all, I know that all the electric fields are the same. I can pull this I off. Everywhere you look, electric field emanating from the surface of the top conductor is going to have the same direction and the same magnitude. I can also write, instead of E dot A sub I, I can actually write this as E times A sub I. So I literally could say that it is A times A sub I. In fact, let me do this in a couple steps. Sorry, you don't have the benefit of the ratio like I do. All right, so let's remember these facts. And let me draw a couple of lines of algebra here. So with these facts, then again, as I just said, electric field is everywhere the same. So there is no distinction between one electric field and the other, so I can just call it a constant. So I can write this as a summation of E, so summation over I of E dot A sub I equals Q enclosed. And again, what's Q enclosed? Q. That's Q enclosed. So that's just Q in upper charge over epsilon naught. And again, from what I just said right here, I can actually write this as the summation over I of the magnitude of E times the magnitude of A sub I equals Q enclosed over epsilon naught. So again, I know that E is everywhere uniform. So there is no distinction. I don't really have to put the I there as a subscript of the E because they're all the same. They're uniform. Okay, and the other thing is because E is parallel throughout, between the plates, they're also it's also parallel to the area normals. So again, the angle between them is 0. So the dot product simply becomes a product, an ordinary product of the magnitudes of E and A sub I. Now the other thing too is I know that if I have a summation and there's a constant multiplying by some distinct variable in the summand, I can actually pull the constant out of the summation. Okay, I showed you that in the previous chapter 18. So I can pull this E out. So I can write this as E times the summation over I of A sub I, again, equals Q over epsilon naught. And, well, what's the summation? I have all these little area patches, that make up this plate. If I add them all up, what do I get? I get the total area of the plate. So quite simply, this simply becomes nothing more than EA equals Q over epsilon naught. So it becomes a very simple calculation because of the very high symmetry in this problem. And finally, I can express for the parallel plate arrangement, I can say that the electric field is equal to the charge divided by epsilon naught A. And in fact, in some cases, some physicists like to refer to the charge over the area as the surface charge density. So some physicists refer to sigma, this is little Greek s, sigma, as Q over A. And they will write this simply as E is nothing more than sigma over epsilon naught. I mean, that's simply what the relationship is for electric field. We're really not going to do that here. We're going to go with this relationship right here. So again, we now know two relationships between electric field and charge. We know the one for the point charge, and now we know the one for a parallel plate arrangement.
So, we've gone from knowing one thing to knowing two things, all right?
So that's very important here. The relationship between the electric field and the charge on that upper plate, electric field that emanates from the upper plate and the charge is given as E equals Q over epsilon naught A. We can add that to our parking lot of what we know, right? And again, this is a direct usage of Gauss's law of electricity. All right, so we have one more thing we know, and now we can actually derive the capacitance. All right, so we know one more thing, that E equals Q over epsilon naught A. Again, this is only true for a parallel plate arrangement. All right, so the top and bottom things, the top and bottom equation are only true for a parallel plate arrangement, whereas the middle relationship is in general true. All right, but we now have the ability. So at this point, here's what I can do. I can now substitute. So I have V equals ED. I can now substitute for E. Directly substitute for E. So what do I get? I get V equals, instead of E, I can put Q over epsilon naught A times D. All I did is made a direct substitution for E. And now let's do a little rearrangement. I want to have Q equals something times voltage, right? So what I'm going to do is I'm simply going to just multiply both sides by epsilon naught A over D. And I do that, I get Q equals epsilon naught A divided by D multiplied by V. And look at this. Q is CV. Q is something times V. So I just derived what the capacitance is for a parallel plate capacitor. The capacitance for a parallel plate capacitor is epsilon naught A over D. Again, parallel plate capacitor. Only. Now this is a very interesting formula, in that you might think that the capacitance would depend on what the material is made out of. It just has to be a conductor. The capacitance only depends on the geometry. All you see there is geometry. I take two conductors and I shape them a certain way, I get a capacitance. That's it. So the capacitance, and you would actually see this for a cylindrical and also a spherical capacitor as well. So the capacitance only depends on geometry. You only see, I mean, again, the epsilon naught is just a constant of the universe. You only see area, so you want to increase the capacitance, what do? Well, you can make the plate bigger, or you make the separation smaller. Again, how do you make a fraction bigger? Well, you increase the numerator, make the area bigger, or reduce the denominator, make this plate separation smaller. All right, and so that's the game you would want to play to try to make the capacitance bigger. So if we were to go do that, for instance, let's just say, for instance, one of the things I like to do when I was a kid, I had a little radio, and I would take it apart, try to put it back together, and take it apart. And I was fascinated that this radio, which I could tune it and play radio stations and everything, it just was nothing but a bunch of circuit elements, a bunch of capacitors, resistors, inductors, wires. That was fascinating to me. And so one of the things you have to do, and this is true all the way back when I was a little kid, is you have to try to make your components small. And so the idea is, well, what are we after? We're trying to get as much charge as possible for a given voltage. So how do you do that? For a given voltage, I want to do what? I want to increase the capacitance, but I want to make things small. So I'd like to try to make the distance, the separation distance, as small as possible. So let's play that game. So for instance, I want to try to make the separation distance as small as possible. Let me kind of rewrite things here. So what are the things we know? So again, we're talking about parallel plate capacitor here. So the object of the game is I want to store charge. That's what a capacitor does. It stores charge. So for a given potential difference across the capacitor, I'm going to store as much charge as possible. How do I make that happen? I'm going to make the capacitance as large as possible. So we want to maximize capacitance. However, we need to miniaturize parts. Okay, so I have the parallel plate capacitor, for instance. All right, so what's my game? Well, so epsilon naught A over D. I want to try to make this as big as possible. Well, it doesn't make any sense to make the area bigger. That makes no sense. So I want to make this plate separation smaller. So I want to make the plate separation smaller to increase the capacitance. But I have a problem. Remember, there's an electric field in between. Remember, there's going to be the electric field. And an electric field is what? The relation between the potential difference in electric field is V equals ZD. So let's see. For a given voltage, that means electric field is V over D. So if I make the distance smaller, I make the electric field larger. So if the distance is too small, so we make the separation, we make D smaller, we make electric field E larger. If the electric field is too large, we get electrical breakdown. Or a spark. You don't want sparking electrons. When you have a thunderstorm outside, that's nothing but a big spark, because you have too much electric field stored, and it's too much for the air, and so you get electrical breakdown. So let's see, how much room do I have? I.e. a spark. All right, so you do not want sparking electronics. So that's the game we have to play. We do want to maximize the capacitance, so we want to make D smaller. However, the issue we have is that the electric field is V divided by D, so we make the D too small, the electric field gets too big, and it could reach the breakdown field and spark. And so that's the game that's the problem you have to have. You can't make it too small. And it turns out that air has a relatively, compared to other materials, air has a relatively small electrical breakdown strength. So how do we get around this problem? Well, we get around this problem by doing the following. All right, so how do we get around this? Well, we're going to stick a material, sandwich a material in the capacitor called a dielectric. So we get around this problem. We get around the electrical breakdown problem by sandwiching a material an insulating material, actually. Between the capacitor plates, called a dielectric. All right, so let's, so instead we'll have, our capacitor plates, positive Q and negative Q, cap Q, and then between we have a material. And it's a dielectric material. And it has a dielectric constant, which we call kappa. Kappa is a Greek letter K. All right, and so I'll show you how all this works out here. So when we do that, we'll find out that our parallel plate capacitor, or capacitance, then becomes kappa epsilon naught A over D. So kappa is actually a unitless number that we have to look up for a given material. So we enhance the capacitance. Now, there's actually a win-win-win situation for using dielectrics. So let's talk about this. Let me bring up OpenStax and let me discuss how a dielectric works. All right, so I need to actually fire up the book real quick. So give me a moment. All right, let's see here. Bring up the book. Oops, hang on. Back it up a little bit here. All right, so give me a moment here. I thought I brought the book up, but I didn't. All right, let me show you a picture of our capacitor, or a parallel plate capacitor with a dielectric sandwiched in between. All right. Sorry, I didn't bring this up before. Okay, so here's my picture. I'll share with you. Okay, share screen. Okay, so what we see here is the parallel plate arrangement, and notice that yeah, the left plate is positively charged, right plate is negatively charged, and what you'll notice is that the atoms that make up, or the molecules that make up the dielectric material are actually they're actually polar, which means they have a positive end and a negative end. The negative ends of the molecules actually will attract to the positive plate, and the positive ends of the molecules will actually attract to the negative plate. So a number of win-win situations are occurring here. First of all, you're actually increasing the amount of charge that's on the plates, because extra charge is getting on each of the plates because of the charge from these polar molecules. And given that we know that E equals, there's an inverse square relationship between electric field and distance. While these charges, a lot of electric fields are actually going to stop short. If you look at the picture on the bottom, only very few field lines actually go across. Most electric field lines that are going to start from the positive charge on the positive plate are going to stop short at a negative end of a polar molecule in a dielectric. And so we know that that's going to create a larger electric field because there's a smaller R. There's a smaller R. So again, electric field depends on KQ over R squared. So a smaller R is going to give you an increased electric field at that location. And the other thing is the electric field lines that are going across, all the way across from one plate to the other, are greatly reduced. Remember, the electric field depends on the number of field lines. Because so many electric field lines that start from the positive plate do not get all the way across, then fewer field lines means that the electric field in the actual capacitor is greatly weakened. Okay, so that is going to help you. That's going to help regarding avoiding electrical breakdown. And on top of that, electrical breakdown strength and air, generally electrical breakdown strength in any kind of dielectric material is going to be much greater than that in air. So let's look at a table here. I'll write some of this stuff down on the board in a moment here. Let's look at a table of dielectric strengths. So notice here that we see that air. The right hand column is the dielectric strength. That's in volts per meter. That's the units for electric field. Air is looks like it is the weakest dielectric strength of all the materials that you see. So you see air is only 3 times 10 to the 6 volts per meter. Other, the next one, bakelite is 24 times 10 to the 6. Fused quartz, 8 times 10 to the 6. Neoprene rubber, 12 times 10 to the 6. Every other material that you could put in between these parallel plates, other than air, has a much greater dielectric breakdown strength. So not only is the electric field going to be weaker because the fewer field lines are going straight across from one plate to the other, but on top of that, the very electric field strength of the material of the dielectric material will be much greater than that of air. So again, it's a win-win-win situation altogether. Now, if you want to look up what the dielectric constants are, I told you, there's this constant kappa. Well, that's in the middle column, and again, kappa, that's what you put in there. So that's something you have to look up. You put that kappa in the formula for the capacitance. So the capacitance is enhanced by that value. So it's multiplied by that value. It's the epsilon naught A over D like it otherwise would be. Then you multiply it by this extra value. All right. And so again, everything is a win-win using a dielectric. So let me stop sharing. Let me back to the board. I'll try to write down what I just said. So again, nothing about a win-win situation using a dielectric. So as we said, so for a given potential difference V, the charge stored on the plates is enhanced. The electric field lines, or the number of electric field lines, going straight from the positive plate to the negative plate is reduced, indicating a weaker electric field. In the capacitor. And even better, the electric field, the breakdown strength, the electric breakdown strength of the dielectric is much greater than that of air. Has a much better ability to maintain electric field. So any way you look at this problem, it is a win-win situation. You get more charge for a given voltage. You have a weaker electric field, and not only that, the dielectric has a greater ability to hold an electric field than air does anyway. Has a greater breakdown strength. So everywhere you look at it, is very it is. I try to not use the word positive because that's when we use positive charge, right? But it is a win-win situation. So what does this mean? Well, essentially, I want to put as much charge as possible, compared with a protector. So again, for a given volt, for a given potential difference, I want to put as much charge as possible. So we can make the separation distance smaller. We can get away with that now. Since E is weaker and that the dielectric material can maintain a larger electric field, also the capacitance C is further enhanced by the dielectric constant kappa, right? So we have that C as kappa epsilon naught A over D. So we have the ability to ramp up the light glare right there. We have the ability to ramp the capacitance. So we can get as much capacitance as possible for a given potential difference, which increases the amount of charge. That's what we're after, and we get to even miniaturize it by keeping the plate separation, keeping the plate area the same, but making the plate separation smaller and smaller. So all of these are great advantages in making electronics. Now one question is, what physically is kappa? That's one thing, one answer. So I have this constant kappa. How do you physically determine what kappa is? All right. So kappa is officially, we can express it as E naught over E. Okay, E naught over E. So E naught is the electric field in a vacuum. E is the electric field strength, I should say. Electric field strength in the dielectric. So volts per meter over volts per meter cancels out. So kappa is unitless. So the dielectric constant has no units. The dielectric constant, kappa, is unitless. All right, keep that in mind. Okay, so let's work a couple of problems out with this new these new concepts. I want to work out problem open section 19.46. Okay, what charge is stored in a 180 microfarad capacitor when 120 volts is applied to it? So a real basic problem. All right, so how do we do this? Well, we use the basic equation. Q equals CV. We know the capacitance. We're given that. We're also told the potential difference. So simple as C is, again, we want to use base SI, so 180 times 10 to the negative 6 farads times 120 volts. So the charge stored on the capacitor with that capacitance and that potential difference will be 2.16 times 10 to the negative 2 coulombs. There you go. All right. Next problem. Let's look at open text 19.51. That says, what capacitance is needed? what capacitance is needed to store 3.00 microcoulombs of charge at a voltage of 120 volts. Okay, again, go back to that original formula, the relationship between charge, capacitance, and voltage, Q equals CV. And again, I want to find the capacitance now, so I need to solve for the capacitance. C is Q over V. So quite simply, the Q is going to be 3 microcoulombs of charge, 3.00 times 10 to the negative 6 coulombs, divided by 120 volts. The capacitance will be 2.50 times 10 to the negative 8 farads, otherwise known as 25.0 nanofarads. That's the capacitor. That's the capacitor I got to pull off the shelf. I got to pull one that's rated at that capacitance off the shelf in order to make that happen. To store that amount of charge with a potential difference of 120 volts. Okay, let me look at OpenStack's 19.54. All right, this says A, what is the capacitance of a parallel plate capacitor? Having plates of area 1.50 meters squared, and are separated by 0.0200 millimeters. Of neoprene rubber. And then B, what charge does it hold? When 9.00 volts is applied to it. All right, so parallel plate capacitor. We're going to design one first, and then we're going to use it. So we'll design it in A, use it in B. What is the capacitance of a parallel plate capacitor having plates of area 1.50 meters squared, that's my A, and are separated by, this would be D, 0.0200 millimeters of neoprene rubber, and I have to look up kappa for neoprene rubber. And then B is what charge does it hold when 9.00 volts is applied to it. Now, I'll know the capacitance, then I apply the voltage, I get the charge, all right? So again, I'm gonna design it in part A and use it in part B, all right? So here we go. real estate purposes, I'm going to erase. All right, so what do I know? Well, again, the formula that for the parallel plate capacitor with a dielectric will be C equals kappa epsilon naught A over D. All right, and so for neoprene rubber, I looked that up in a table. I find out the kappa is 6.7. Neoprene rubber. I have to look that up. I was given the area A, 1.50 meters squared, and I'm given the separation of the plates D of 0.0200 times 10 to the negative 3 meters. I'm given all of this information. All right. Now, it is a simple matter now to calculate C. So C is going to be kappa, which is 6.7 epsilon naught. So permittivity of free space, constant of the universe, constant of the universe of 8.85 times 10 to the negative 12 Coulomb squared per Newton meters squared. A is 1.50 meters squared and divided by D. All this is divided by D, which is 0.0200 times 10 to the negative 3 meters. When I do that, I find out that the capacitance is 4.45 times 10 to the negative 6 farads, otherwise known as 4.45 microfarads. A typical capacitor, capacitance. All right, there's your part A. And of course, I've now designed the parallel plate capacitor. I now know what the capacitance is. I can predict that very easily. Part B means I'm now going to use it. So now I want to figure out how much charge is on that capacitor when I apply a certain potential difference. So charge is Q equals CV. So I figured out C, so that's 4.45 times 10 to the negative 6 farads times the voltage of 9 volts, 9.00 volts. And I find out that Q is going to be 4.0 times 10 to the negative 5 coulombs. There you are. So again, I designed the capacitor and I use the capacitor. All right. So as I said earlier, the capacitor is one of the 3 circuit elements we will study in this class. And then we'll study the capacitor, the resistor, and the inductor. So when we use the capacitor, we want to put it into a circuit. All right, and so we'll find out that we can actually, there's a couple different ways to connect circuit elements in a circuit. So there are 2 major ways to connect circuit elements. In general, I call them circuit elements. I mean, they include the capacitor, resistor, and inductor, among others. And we don't know what these other 2 are yet. All right. So there are 2 major ways to conduct circuit elements: the capacitor, resistor, and inductor. One way is a series connection, and the other one is a parallel connection. You can connect circuit elements either in series or in parallel. So we're going to study connecting capacitors in series and in parallel. And then in chapter 20, we'll do the same for resistors. All right. So first of all, let's talk about series. So let's connect capacitors in series. I'm going to draw a picture. Now, again, I'm going to start off with a battery. Battery has two terminals, a positive and a negative. All right. And then what we're going to do is we're going to imagine taking a wire. And we're going to have now when you look at an electrical schematic, there are symbols that represent different elements. The one that represents a capacitor looks like parallel plates, or it looks like, I always think it looks like captain bars, on an army office, or army captain, it looks like captain bars or parallel plates. Or basically two parallel plates for, that represent a capacitor. I'm going to hook up 3 capacitors. All right, and then bring the wire back like so. I will call the capacitors C1, C2, C3. Now, we'll find out later on that the symbol for, so this is a symbol for a capacitor. We'll find out later on that the symbol for a resistor looks like this. And the symbol for an inductor looks like a coil. Inductor is given by the letter L, inductor. So we'll talk about that when the time comes. But anyway, capacitor, resistor, inductor. Right now we're talking about capacitor. So when you make a schematic, it's basically a line. The lines represent circuitry of wires, and then you're putting on the schematic. Basically means that you have a wire hooked from the positive terminal, and you're going to connect it to a capacitor, then connect that capacitor to the second capacitor, and then connect the second capacitor to the third capacitor, and then finally you're going to connect the third capacitor back to the negative terminal on the battery or the power supply. All right. So now, when we say series, we mean that the circuit elements are going to be connected across the same circuit path. All right. So what we mean by this is that the circuit elements, the capacitors, well, let's just say in general, because this will be true for resistors as well. Circuit elements are connected across or connected along the same circuit path. Okay, one path, one wire goes through. This is a single path that goes through these 3. In this case, the circuit elements are capacitors. But in general, I could write resistors here. I mean, again, it's circuit elements connected along the same circuit path. That's what series means. All right, so that's what series means. And what I want to do is I'd like to actually try to figure out how I can replace these 3 capacitors that are connected in series with one corresponding capacitor. I'd like to find out, can I make an equivalent circuit where I only have to use one capacitor? So I'd like to do the following. I like to have my same battery. But instead, I like to have one capacitor. I'll call it C, and I'll put a little S for series. I like to actually have some where the two are equivalent to each other. All right, that the left arrangement is equivalent to the right arrangement. How do I do that? Well, first of all, one of the things I have to understand is that when I connect, just like I showed you earlier, when I connect a capacitor to a battery, what happens is I get a separation of charge. I get a plus Q and a negative Q. Now, I'm going to have a separation of charge on these capacitors as well. It turns out that because of the conservation of charge, each of these capacitors has the same charge separation as the total. All right, so by the conservation of charge, each capacitor has charge separation plus cap Q and negative cap Q, which is the same for each capacitor, and for the equivalent capacitance or capacitor C sub S. The job of a capacitor is just to separate charge. And so they're going to separate the same amount of charge. If you cannot have a different amount of charge being separated. Again, that would cause there to be an imbalance in the charge. They all have to be separated by the same plus Q and minus Q. That's the thing to keep in mind. That's governed by the conservation of charge. Conservation of charge determines that. So one of the things that I also want to understand in a given circuit element is given, I always want to be able to relate it to the potential difference. So every circuit element has to have a relationship of how the potential drops across that circuit element. So we understand that relationship for the capacitor. We know that Q equals CV. All right, and so we know how that works. We know that the potential is going to be Q over C. Turns out when it comes to resistors, it depends on current, which is flowing charge. And so it has a relationship that relates to the current, and so on and so forth. And so, and for inductors, it'll be the time rate of change of the current. Again, we'll get to that at the time, in proper time. So the potential by the conservation of energy, remember the potential is only different from energy by the division of a charge. So remember how we got potential? The potential is nothing but the work or the potential energy or also the potential energy, change potential energy per charge. So it's an energy per charge. So conservation of energy applies here, and it can show up in the terms of of potential. Again, because there's only the difference between one and the other is just a division by a constant, right? And so by the conservation of energy, if I say that the potential across the battery is V, then there's going to be a potential across Q1, we'll call it V1, C1, we'll call it V1, across C2, we'll call it V2, and across C3, we'll call it V3. So that means by the conservation of energy, V, the potential across the battery has to be the sum of the three potentials. V1 plus V2 plus V3 as you go around the circuit. Again, you'll get a potential increase from the battery, and you'll have a potential drop across each circuit. By the conservation of energy, this relationship has to hold. Okay, that's by the conservation of energy. So if we know the potential, and again, this potential across the battery is the same as would be the potential across the corresponding series, the equivalent capacitance. Because the potential, there's only one thing to balance it out. The increase has to, the increase has to be equivalent to the drop. There's only one potential to balance it out. So again, if there's only one potential on the other side of the equation, then one has to equal the other. However, we have three potentials, and so we have the summation. But if there's only one capacitor, you wouldn't have these other two terms, and you'd have one potential equaling the other. And that's the case here. So that also would be the potential across the battery. So that potential, now across this battery is a potential that would be across the equivalent capacitor. So putting this together, we see that we can write this as Q over C series equals Q over C1 plus Q over C2. Let me write this differently. I have a little glare right there. All right, so again, this would be written as Q. This comes out as Q over C series equals Q over C1 plus Q over C2 plus Q over C3. All right, and so these Q's cancel out. And so we would see that I would add, in series, I would add capacitors like this. That 1 over C series, right on the right spot there. 1 over C series is equal to 1 over C1 plus, write this out. So again, altogether, I would write for capacitors in series that 1 over C series, the total equivalent capacitance, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And if there are more capacitors in series, I would just keep on doing that. So what I would do is I would take the capacitors that are connected in series, 1 over, and I'll show you some examples of this, 1 over the first, plus 1 over the second, plus 1 over the third. Then altogether, after I add up all of these inverted capacitances, then I'd have a summation. I would flip it to get what the equivalent series capacitance is. So again, this circuit is exactly equivalent to this circuit. Basically, instead of having these three capacitors in series, I can actually put this capacitor in there instead, and it'd be equivalent. Now, one of the things about capacitors in series is that the total series capacitance C sub S is smaller than the capacitance of any of the capacitors involved in the series connection. All right, and so that's one thing to keep in mind here is that when you add capacitors in series, the total equivalent, the equivalent series capacitance C sub S is smaller than the capacitance of any capacitor involved in the series connection. So the total capacitance here is going to be smaller than any of C1, C2, or C3 when they're connected in series like this. All right, now, the next connection is what's called a parallel connection. All right, and also one thing to keep in mind here is that the way I drew this is that there's going to be an equivalent larger spacing as well. So again, D epsilon A over D, D is going to be bigger, so this capacitance will be smaller as well. It's one way to look at it geometrically. All right, now let's connect capacitors in parallel. Let's see what that looks like. All right, parallel connection. So again, I want to have an equivalent circuit. So I'll change this S to a P for parallel. And what does a parallel connection look like? So again, I'll change my picture around. I'll have three capacitors like I did before. And what I'll do is I'll connect them like so. Okay, so they're going to be connected in this manner. I have C1, C2, C3. Now, what's different here is that, remember, wires are made out of metal, which are conductors. This wire up here is the entire wire all the way across is an equipotential. Remember, a conductor is an equipotential. And this wire all the way in the bottom is also an equipotential. That means that two wires, these two wires are connecting. Each of these capacitors has the same potential difference across them. It's going from this constant potential to this constant potential all the way across. So each one of them has the same potential difference across them, and it's the same as the potential difference across the battery itself. So each one of these has a potential across it of V. All right, why? Because it is across the same equipotentials. The concept of an equipotential is extremely important in doing circuitry. So again, each capacitor, so the top and bottom wire branches this is what it means to be connected in parallel. The top and bottom wire branches are equipotential lines. So the same potential difference is across C1, C2, and C3, which is the same as across the battery terminals. We call that V. So all of these, so the potential across the battery terminals is V. The potential across each of these capacitors is also V. Now we will now employ the conservation of charge. We realize that there will be a charge separation Q, across, let's say, the total equivalent parallel capacitance. However, we have a decision to make at this point. This is called a junction. This means you have total charge, but some charge can go across. It'll be split up. Some will go across capacitor C1, some will go across capacitor C2, and some will go across capacitor C3. So the charge forms a junction. So that means that you'll have, let's say, a plus Q1 minus Q1 plus Q2 minus Q2 plus Q3 minus Q3, such that by the conservation of charge, at a junction, Q must equal Q1 plus Q2 plus Q3. Again, this will become even more understandable when we have current flowing in. The current will have to make a decision. Do I go here, here, or here? There's three different branches. So much charge is going to go to capacitor C1, so much charge to capacitor C2, so much charge to capacitor C3, but the total charge, let's say right here, would be capital Q. So again, there has to be a decision made at a junction so they separate themselves out. So the equation that is the important equation here is the equation at the junction, again, for a parallel connection. So the junction equation is going to be Q is Q1 plus Q2 plus Q3. There's a decision to make. Here's the charge, the total charge, but again, some charge has to go through Q1, some through Q3, and some through Q3. Again, they are not on a common circuit path. They are split, they are parallel. And so there are three different roads to take. And so some charges, an amount Q1 will go through capacitor C1, that branch. Some but amount Q2 will go through the branch through capacitor C2, and some of amount Q3 will go through the branch for C3. They are not along a common circuit path. They're in parallel paths. Now, remember what the relationship is. Q equals CV in general for a capacitor, the voltage charge relationship for a capacitor. Well, they all have the same. They all have the same potential difference across them. So I could literally say, well, I have C parallel V equals C1V plus C2V plus C3V, and all the V's cancel. They all have the same potential across them. So for capacitors in parallel, it is quite simple. For a parallel arrangement, capacitors in parallel simply add C1 plus C2 plus C3 plus dot, 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 if I have more capacitors in parallel. Again, these are capacitors connected in parallel. So the equivalent circuit with a capacitor C sub P, well, it would be arrived at by literally just adding up all the capacitors that are in parallel. So it's very simple. All right, so this is an equivalent circuit. This is an equivalent capacitor to these three. Instead of having these three hooked up in parallel like this, I could just have the equivalent capacitor for this, just put equivalent capacitor, and literally I could determine that by just adding up the three capacitances. All right, so to summarize, again, I can connect circuit elements in parallel or series. Capacitors in series. I can get an equivalent capacitance by, I'll use S for series. C sub S is just, oops, I'm sorry. I have to add it in this funky way. 1 over C sub S is 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot. And we'll go through some examples. I'll go through some problems to show you this. And for the ones in parallel, capacitors in parallel, we get simply the equivalent parallel capacitor that I could put in there instead of the ones that are connected in parallel. It would literally just be C1 plus C2 plus C3 plus dot, dot, dot. So literally you would just add them. So simple as that. All right, so again, you have capacitors in series. The equivalent capacitor, I can rip out the capacitor in a series and put one capacitor in. I would arrive at figuring out that capacitor through that capacitance through this relationship. And if I have capacitors in parallel, I want to rip those out and put one capacitor that represents it. I would find that in the following manner by simply just adding up all the capacitors that are added in parallel. All right. So what's left to do for the rest of this lecture is just work out a few problems and then call it a done deal. All right. So here's the name of the game. So let's look at OpenStax 19.57. All right, that says find the total capacitance. Of the combination of capacitors. In figure 19.33. All right, so I have a combination. So I have basically going to, we're going to pull it out of the circuit. So I have two in there that are in parallel. They come back together to the main spine, main branch. And then I have another one that's connected in series to this parallel combination. All right, so there you go. So we have C1, C2, C3. I'm given that C1 is 10 microfarads. C2 is 2.5 microfarads. C3 is 0.30 microfarads. Now, when you break down circuits like this, or you break down circuit elements like this, you really just have to do it in a systematic way. I mean, you might look at a set of capacitors and be kind of intimidated by it, but you just have to do things in a very systematic way. So, first thing I want to do to simplify this circuit, again, every single circuit I will draw is equivalent to the previous one. So, what I want to do is say, okay, well, I have two capacitors that are in parallel. And what I want to do is I want to draw another circuit. It looks like this. I'm going to combine these two that are in parallel. I'll call it C12, and I'll leave C3 alone. And so I really want to make this particular new circuit. This is the equivalent circuit. How do I figure out C12? Well, what's nice is the ones that are in parallel simply just add, right? So C12 is nothing more than C1 plus C2. So C12 is going to be what? 10 microfarads plus 2.5 microfarads. C12 will be 12.5 microfarads. All right. So I can put this in my little parking lot here. I have C12, which is 12.5 microfarads. That's all the two add. All right, great. So this is now a perfectly equivalent circuit. This circuit is totally equivalent to this circuit. All right, so I can probably just, here's my little evolution here. So I have this circuit here. I'm just making the circuit as simple as possible. Now, what I really want to do is I want to have the equivalent circuit that represents, the equivalent capacitor represents this original combination of capacitors. So what I have left now are two capacitors that are in series, and I really want to create, in final, I want to create one capacitor. And I'll just call it C total. And the question is, how do I get to C total? Well, I have to add up this weird way, right? So 1 over C total is going to be 1 over C12 plus 1 over C3, because that is how capacitors connected in series add. All right, so 1 over C total. C12, remember, is 12.5 microfarads. So 1 over 12.5 times 10 to the negative 6 farads. Plus C3, 1 over 0.30 times 10 to the negative 6 farads. All right, so if I do this, let me just go to my calculator here to help you out. So again, let's separate this. So if I do this, I go to my calculator, and all right, so I have two numbers up. I have to go 1 divided by 12.5, 10 to the negative 6. That's 80,000. So this first number is going to simply become 80,000. Plus this next number. 1 divided by 0.3, 10 to the negative 6. Again, in your calculator, you're going to get a big number, 3333, you know, so a whole bunch of, you know, it's going to be 3333, bunch of threes, 1, 2, 3, 4, 5, 6, 7. 0.333 in your calculator. So you're going to add these two up. You're going to have this number plus this number. You will find out that when you add these up, I'm going to erase the original picture here for real estate purposes. When I add these two up, I will find out that 1 over C sub t is going to be some big number, 341, 4 3s, 0.333. Again, I'm just being ridiculous here, but I'm just trying to give you a feel for what you should be seeing in your calculator. But that's not the answer that I want, right? When I add these up, I'm getting a huge number, but that's 1 over C sub t. What I want is C sub t, so I'm going to flip this upside down. So C sub t will be 1 over this big number. So take the -1 on that, and that's going to be 2.93 times 10 to the -7 farads, or C sub t will be 0.293 microfarads. So again, I took the first, you don't see the picture anymore, but I combined C1 and T2, and I just simply added them up to give you C1, 2. Equivalent couple of capacitors, equivalent to the 3 that I originally wrote down. Then I have 2 capacitors that are in series. I can combine them to create C sub t, but I have to combine series capacitors in this funny way of adding. 1 over C sub t is 1 over C1, 2 plus 1 over C3. So again, I'm going to be expecting very big numbers I'm going to be adding together in my calculator. So this first one's going to give me 80,000. The second one's going to give me this 333, a whole bunch of 3s, 0.333, right? When I add them all together, I'm going to get this giant number in my calculator. But again, that's 1 over C sub t. That's not the capacitance. I have to flip it upside down to get the actual equivalent capacitance of this combination. And so when I do that, I get 2.93 times 10 to the -7 farads, which would be 0.293 microfarads. So again, definitely go through this in your calculator to understand how you add these capacitors in series. I mean, it's different. You have to add the multiplicative inverses. That's what you have to do. That's how you add capacitors in series. All right. I'm going to do 2 more problems, and then we'll call it a done deal. All right. 19.58. That's the next problem I'm going to do. OpenStax 19.58. That one says, suppose you want a capacitor bank. With a total capacitance of 0.750 capacitors. farads. And you possess numerous 1.50 millifarad capacitors. What is the smallest number you could hook together to achieve your goal? how would you connect them? All right. So I have a bunch of 1.50 millifarad capacitors on hand. I want to try to connect them together in such a way, either series or parallel, in order to be able to make a total capacitance of 0.750 farads. Okay, so first of all, the total capacitance that I'm trying to achieve is bigger than the capacitance of any of the involved capacitors. So that tells you right off the bat that they cannot be connected in series. So remember, capacitors in series, when you connect a bunch of capacitors in series, the total capacitance is smaller than the capacitance of any of the involved capacitors in that series connection. So I do not want to connect them in series. So I'm going to want to connect these all in parallel. All right. And again, in parallel, when I connect that capacitor in parallel, they simply just add up. So I want the minimum number. So I'm going to connect them all in parallel. All right. So kind of write down what I just said. The goal total capacitance is greater than the capacitance of any capacitors involved. All right, so you do not want to connect them in series. Since total capacitance, the total capacitance of capacitors in series, so the total capacitance of capacitors connected in series is smaller than the capacitance of any capacitor involved in the series connection. So we want to connect the capacitors in parallel. Okay, so number one, we want to connect them all in parallel. All right, and so the question is, okay, well, we know how parallel connections happen. We know that we would just literally add them all up. Well, they're all the same. So again, a capacitor in parallel is going to be, C1 plus C2 plus C3 plus ... But all involved capacitors have capacitance C equals 1.50 millifarads. right? And so adding them all up is as simple as this. The total parallel capacitance is going to be NC, where N is the number of capacitors. C sub P is going to be 0.750 farads. So literally, I want to figure out how many capacitors I've had to hook up in parallel. It would be the N is simply going to be C sub P over C. Or it would be 0.750 farads divided by 1.50 times 10 to the negative 3 farads, which, if you do that, you find out that that's going to give you N equals 500. 500 capacitors. So if I connect 500 of these 1.50 millifarad capacitors together, I can create a capacitor bank that's equivalent to 0.750 farads. And it takes me 500 of these capacitors to do that. All right. We have one more problem, and this is going to be a long one. Again, this is going to be one of these typical complicated circuit type problems. All right. So I'm going to do OpenStax 19.61. And we'll call it a done deal. So this is typically what kind of a combination is more representative. We've been fairly simple up till now, but let's kind of take one that's going to be more complicated. So we want to find a total capacitance of the capacitor shown in figure 19.35. So find the total capacitance of the capacitors shown in figure, and this is a figure out of OpenStax, 19.35, all right? So that's all we're gonna do. I'll draw the figure here in a moment here. I need as much real estate as possible, so I'm gonna erase these words. We just want to, again, we're gonna get an arrangement of capacitors, and we want to get the equivalent, total equivalent capacitance. And we're just gonna connect series and parallel combinations and finally get an equivalent, all right? So the original picture looks like the following. So I have a little spine here and cross. Okay, I have a capacitor in the middle, and on the side I have a couple of capacitors. And over here I have a capacitor, and then I branch. Let's see, I have another capacitor here. And I branch off, and I have another capacitor on the side. All right, so the capacitors here are going to be, I'm going to call them C1, C2, C3, C4, C5, and C6. All right, so I have all these capacitors in this arrangement. I really want to eventually get down to, instead of this big arrangement of capacitors, I'd like to just have one capacitor that's equivalent to all of these. So how do I figure this out? Well, it's just a matter of looking at them and just drawing equivalent diagrams and whittling it down to what I want. So I look at this and say, okay, now first of all, I need to state what my actual values are. So again, I have C1 is going to be 5.0 microfarads. C2 is going to be 3.5 microfarads. C3 is 8.0 microfarads. C4 is 1.5 microfarads. C5 is 0.75 microfarads. C6 is going to be, let's see, is 15 microfarads. All right, so here we go. These are all capacitors that I hooked up. Now, I want to try to get the equivalent. So it's going to be an evolutionary process to just simplify this diagram. So I look at it and say, well, I mean, I could basically make several choices. I think the first thing I want to do is I see these parallel capacitors are really easy to combine. So I see the C5, C6. So why don't I just combine that? So let's make a new equivalent diagram. In that diagram, I'll have my central spine again. And on the left, I'll still have C1 and C2. But here on the right, I'm going to have C4, and I'm going to have what I call C5, 6. All right, so again, this will still be C1, C2, C3. I guess C3 is more central. C3, C4, and this is now C5, 6. All right, how do I get C5, 6? Well, again, these two capacitors are in parallel. They add up really easily, right? So capacitors in parallel, C5, 6 is just C5 plus C6. Simple enough. So C5, 6 is going to be, C5 is 0.75 microfarads plus C6 is 15 microfarads. And so simple math says that that's 15.75 microfarads. Great. So I'll put that on my little parking lot. C5, 6 is 15.75 microfarads. All right. So this diagram is totally equivalent to the first diagram. Now, unfortunately, because of my real estate problems here, I'm gonna have to constantly be erasing diagrams. Normally, if I was doing this face to face, you would see a whole series of diagrams all the way across the whiteboard. But unfortunately, I don't have the ability to do this. I have limited whiteboard space. So this is my latest and greatest equivalent diagram. Instead of drawing this diagram, I could draw this diagram. They're perfectly equivalent capacitors. Now, what I want to do now is my next evolution. I want to simplify this diagram further. So I think what I like to do, the next thing I would like to do is combine C1 and C2 to make C12, and combine C4 and C5, 6 to make C4, 5, 6. And unfortunately, I'd have to combine that such that they're in series. So I have to add up that weird way. So what I want to do is I want to now make my next diagram look like this. My next diagram, so again, it's going to be a series of diagrams as you move along. The next diagram, I have my central spine again. In this case, I have here and here. Okay, this will be C12. This would be C12, C3, C4, 5, 6. Well, how do I get those? Well, again, I have to add them the weird way, remember? I have to add them that 1 over business. So again, I would get C12 by saying, well, 1 over C12 is 1 over C1 plus 1 over C2. Or 1 over C12 will be 1 over C1, which is 5 microfarads, plus 1 over C2, which is 3.5 microfarads. 3.5 10 to the negative 6. If I go to my calculator, 1 over C12, well, if I take 1 over 5 times 10 to the negative 6 in my calculator, I get 200,000. All right, and then 1 over 3.5 10 to the negative 6. Oops. 1 divided by 3.5 10 to the negative 6. I get some other big number, 285,714. 0.2857. So again, some big number. Okay, so two big, huge numbers I'm going to add together. All right, so I add those together, and I get 485,714. So again, I'll get 1 over C12 is a 485,714.2857. Again, I'm just writing this just for effect. I mean, that's the kind of number you should be expecting in your calculator. But that's not what you want. Again, that's 1 over C12. You want to flip that number upside down. And what you're going to get is, when you flip it upside down, you get the C12 is 2.06 times 10 to the negative 6 farads. Or that's 2.06 microfarads. So again, you have to add it in this, because they're in series, you have to add it in this, inverse way. 1 over C12 equals 1 over C1 plus 1 over C2. 1 over C12 is 1 over 5 times 10 to the negative 6 plus 1 over 3.5 times 10 to the negative 6. 1 over C12, you're going to get the addition of two big numbers like this. And so that's going to give you the sum of two big numbers is a bigger number. But again, that big number is equivalent of 1 over C12, which is not what you want. You want C12. So you'll flip it upside down. You get a small number, 2.06 on 10 to the negative 6 farads, or 2.06 microfarads. So we'll put that on our parking lot. That C12 is 2.06 microfarads. Okay? I got to find one more capacitance. And I need to get C456. I got to find it the same way I got this one. All right? So again, find that capacitance. So very similar calculation. All right, so that'll give me 1 over C456 is 1 over C4 plus 1 over C56. All right, so 1 over C456. 1 over C4. C4 is 1.5 microfarads. 1.5 times 10 to the negative 6 plus 1 over C56, 15.75, 10 to the negative 6. 1 over 15.75 times 10 to the negative 6. So again, in my calculator, 1 over C456, big numbers. So again, 1 divided by 1.5, 10 to the negative 6. I get 6 sixes, 0.6667. So 66666.6667 plus 1 over 15.75, 10 to the negative 6. I get some other big number. I'm just writing this for effect. Plus 63492.06349. Okay, two big numbers being added together. When I add that all together, these two big numbers, a big number from this term, big number from this term. I add these two big numbers together, I get 1 over C 4, 5, 6 is going to be, well, let's see here. I'm going to get this plus 1 over 1.5, 10, 6. I get like 730,158. 0.7302. Again, I'm just writing this all for effect. That's what my calculator says. Again, I don't want that big number. I want the inverse of it. So C456, flipping both upside down, taking the inverse of each one, I find out that it's going to be 1.37 times 10 to the negative 6 farads, which is 1.37 microfarads. Great. That is what I want now. So in my parking lot, I'm going to put in C456 in my parking lot. So C456, among all the things I know, is going to be 1.37 microfarads. All right, so now I know C12, C456, and I know C3. What I want to now do is combine them all to give me one final capacitor. So I'm going to finally write one last diagram, which is simply looking like this, C total. And these, again, this is an equivalent capacitor arrangement to the original one, or actually the original two that I already drew. I'm just evolving the diagram. What I'm now going to get is one simple capacitor is going to represent everything that I originally had. So now what I have left in this process is I just have 3 capacitors that are in parallel, and of course that adds up very easily. So in parallel, I would simply get that C total is nothing more than C12 plus C3. I finally get to use C3 plus C456. And so finally, C total is going to be my C12 is 2.06 microfarads plus my C3 is 8.0 microfarads plus my C456 is 1.37 microfarads. It's literally adding up these 3 numbers. So the final total capacitance, if I took my entire original arrangement and just ripped all that out and had one capacitor representing everything, it would be the summation of these 3, and I would get 11.43 microfarads. So one 11.43 microfarad capacitor would be equivalent to the entire original arrangement that you saw. Instead, I can literally just have one capacitor that represents everything. All right. So again, that is how, and again, you'll do similar type of work with resistors. Again, the idea is, recognizing series and parallel connections. All right, we have one last concept that I want to talk about before we call this quits, and that is energy storage in a capacitor. So a capacitor stores charge, but it also stores energy. So energy stored in a capacitor. Final topic. Okay. Now, energy stored in a capacitor is electrical potential energy. And so it is related to the stored charge, cap Q, and the potential difference V across the capacitor. Okay, so, but be careful. Be careful. You cannot just write down that the potential energy is QV. You might be tempted to do that. You might say, oh, well, there's a charge Q and a potential difference V. It's Q times V. Well, it's not. And we have to be careful not to say that. So why is it not Q times V? Well, let's look at the process. So again, initially, there's no connected battery. Okay, so initially, before the battery is connected to the parallel conducting plates, so before the battery, so remember, it takes a battery to be connected for anything to happen. So before the battery is connected to the parallel plates, conducting plates, the plates have no stored charge. And hence, no potential difference across them. Okay, so again, we're starting off with everything being 0. All right, now we connect the battery. After, I'm going to do things in this super slow motion here. After we connect the battery, the first charge to arrive on the plates feels no potential difference. Feels a potential difference of 0. There's no charge there before it. The last charge to arrive at the plates feels the full potential V. All right. And so again, there's a buildup. There's a buildup of charge and a buildup of potential. All right, and so the more important thing to do here is to take a look at the average. Now, again, we're avoiding integral calculus. You know, there really is an integral that needs to be done here. We're avoiding that. So, so the average voltage on the or potential difference on the capacitor is right in between 0 and V. And that's V over 2, 1/2 V. That's the average. And so the energy stored, so thus the energy stored on the capacitor, or in the capacitor, I should say, or in a capacitor, is not QV, but is E sub cap, is QV divided by 2. That's what it is. It's Q times the average potential. Now, we have a couple other ways of writing this as well that are equivalent. We could say instead, well, let's utilize the relationship Q equals CV for a capacitor. So we could say, well, let's substitute for Q. If we do that, we could write that E cap is, again, they're all equivalent. We can write that E cap is also 1/2 CV squared. Or I can substitute for V. V equals Q over C. And so I can also write that E cap is Q squared over 2C. There are absolutely 3 equivalent ways of writing the energy stored in a capacitor. And the idea is, well, which one do you use? Well, you use the one that you know about. In general, the one I see used the most is 1/2 CV squared. Why? Because I can usually pick a capacitor off the shelf and know what its capacitance is. And measuring potential difference with a potentiometer or a voltmeter is really easy to do. So I usually can very easily know what C and V are, and I can find the energy stored in the capacitor by using 1/2 CV squared. It is harder to know what the charge Q is. So these two are ones that are not used as often. The one that's used most is the form 1/2 CV squared, but they're all 3 equivalent. And I just pick one because of what I know. Okay, that's the energy stored in the capacitor. I'm going to work out one energy problem and then we will call it done. All right, so I'm going to work out OpenStax 19.63. Again, an idea about this. All right, OpenStax 19.63. That says A, what is the energy stored? In a 10.0 microfarad capacitor in a heart defibrillator charge to 9.00 times 10 to the third volts. And then B, what is the amount of stored charge? One of the nice things about OpenStax is that it's very much geared toward people who are going to go into medicine. And so you see things like heart defibrillators, things like that. You know, because this class is more or less geared to people who are going to be medical professionals or people who are in the biosciences. So they make note of that, and they make a lot of examples of medical applications. So again, A, what is this energy stored in a 10.0 microfarad capacitor in a heart defibrillator charged to 9.00 times 10 to the third volts? And then B, what is the amount of stored charge? So again, I have three choices to make as far as the stored energy is concerned. I can just put it all here. And so what do I know? Well, I know the capacitance and I know the voltage, so I'm going to want to pick 1/2 CV squared. That's what I know. So E cap is 1/2 CV squared, or 1/2. The capacitance is 10 microfarads. And then V squared, well, 9.00 times 10 to the third volts squared. If I do all this in SI units, I should get joules. E cap, when I do this, it's going to be 405 joules. That's how much energy is stored in a 10 microfarad capacitor when there's 9,000 volts across it. And then B, what's the stored charge? Well, I use the basic formula for the capacitance, Q equals CV. And I get that that's going to be, C again is 10.0 times 10 to the next -6 farads times 9.00 times 10 to the third volts. And I get that Q, the stored charge, is going to be 0.090 coulombs, or otherwise 90 millicoulombs. All right, that is the answer. So again, energy stored in the capacitor and the amount of charge stored on the capacitor plates. And that is all I have for this lecture.